Hi, everybody. Before we start today's lesson, let's look at this warm-up question. This is an SAT question that fits right along with what we're talking about now in this unit. So it says the function f is defined by a polynomial. Some values of x and f of x are shown in the table. Which of the following must be a factor of f of x? So what we want you to do is pause the video, see if you can figure out the answer, and then when you're ready to check your work, hit play. Okay, so let's look and see here. Our first hint that we want to give you is which one is a solution root and zero. Solution root zero, they mean the same thing. But you know what else means the same thing as solution root zero? X-intercept. X-intercept. So I look at my table and I say, is there an x-intercept on my table? X-intercepts are where y is 0. So I look and sure enough, there we go, 4, 0. That is our x-intercept, but it's also a solution root 0. Okay, so if a is a root, then x minus a is a factor. So my SRZ is 4, so x minus 4 must also be a factor. Okay, on today's notes, we are going to be looking at an application problem. And then after we do the application problem, then we will let you get started on your review. So here's the problem. It says an open box is to be made from a 10-inch by 12-inch piece of cardboard by cutting X-inch squares in each corner and then folding up the sides. Write a function for the volume of the box in terms of X. Approximate the volume X, which is the height that produces the greatest volume. So, the first thing we need to do that we learned about in geometry is that we need to draw and label a picture. We can't go anywhere until we draw and label a picture. So we start with a 12 by 10 inch piece of cardboard. Then from each corner, we are going to cut a square that is an X by X in dimensions. So the green illustrates the square that's going to be cut from each corner. So when we remove those corners, it looks like this. Now, if my whole side was 12 and I took a length of X off each end, then the new side would be 12 minus 2x. Looking at the 10 side, same thing. If I have a 10-inch side and I take an x off each end, then my new dimension is going to be 10 minus 2x. And then, of course, the pieces that I've cut out are both x by x. So this is the picture of the figure unfolded. But what does it look like when we fold it? Okay, so this is what our box looks like folded up. Our base has a length of 12 minus 2x and a width of 10 minus 2x. And then, of course, x is the height because that's the part that was cut to fold up to make the box. So part B says we need to write an equation in factored form for the volume as if the box was closed. Well, we know volume equals length times width times height. So I have 12 minus 2x times 10 minus 2x times x. So that is your equation in factored form. Now that we have the graph in factored form, we can find the roots. Because remember, from factor form, we set each factor equal to 0, and then we solve for x. Because basically, kind of let me tell you what we're doing. We're taking this information about the box, we're going to turn it into a function that we graph, and then that's in turn going to help us find the biggest x that would maximize the volume. So all of that stuff we just did was to get us to this point of writing the factored form of the equation. So we're going to take and set each factor equal to 0. So 12 minus 2x equals 0. That gives me x is 6. 10 minus 2x equals 0. That gives me x is 5. And then x is 0. Now I know what you're going to say. You're going to say, shouldn't you write those in order? And you'd be correct. The only reason we wrote them out of order is just so you could see what comes from what. So the 6 comes from the first factor, the 5 comes from the second factor, and 0 comes from the third factor. Okay, so now that we found our roots, we're going to plot them on our graph. So there are my roots. All right, now that we have completed step 1, which was to find the SRZs and plot them, now we're going to be talking about end behavior. But for end behavior, we need the leading term of our equation. And to get the leading term, our equation needs to be in standard form. So I'm going to first multiply those two binomials together. Then I'm going to distribute the x. But when I distribute the x, I'm also going to take that opportunity to write it in standard form. So I end up with v of x equals 4x cubed minus 44x squared plus 120x. So I'm going to circle my leading term, which is 4x cubed. So I first look at the A term because A determines right end behavior. A is positive, so positive means that right end goes up. So from my rightmost 0, I'm going to make the graph go up. Then I look at the exponent, the n. The n is odd, and odd means opposite. So the exponent is left end behavior and it's opposite of the right end. Well, right end is up, so that means left end is down. So I go to my leftmost 0 and I make the graph go down. Now, step 3 is typically find your y-intercept, but I already have an x-intercept of 0, 0, so that actually is also the y-intercept as well. So now I can move on to finding the relative max and min. Now you can use your TI-84, you can use Desmos, whatever is the easiest for you. So we're going to find that relative max and min, we're going to plot those points, and then we're going to connect the dots. So I find that my relative max is 1.811, 96.771. Now, could I have rounded that point to 1.8 and 96.8? Absolutely, because it's going to be graphed in the same location ultimately. Now, you will notice that I have scaled my volume by 30. I have scaled my volume by 30. So each tick mark on the y-axis represents 30. So I'm going to go plot 1.8, 96.8. And don't forget to label it. Then I'm going to repeat the process for the relative minimum. And I find out that the relative minimum is 5.523 and negative 5.511. So again, round it, yeah, 5.5 to negative 5.5. And again, because my scale is in 30s, that's going to be really super close to the x-axis because I'm scaling by 30s on the y. Now we're going to do a fancy game of connect the dots. So this asks the question, what is an interval of possible values for x? possible values for x. Well, this curve represents the volumes that are created by taking different side lengths of x off from each corner. So x also represents the height of your polynomial. I'm sorry, not your polynomial, of your box. The x represents the height of the box. So if this curve represents volume, then when my curve is above the x-axis, that means that my volume is positive. When my curve is below the x-axis, that means that my volume is negative. So the only place my curve is above the x-axis, so we're looking right here at that circle. The only place where my volume is positive is between the x values of 0 and 5. So when x is between 0 and 5, then I know that my volume is going to be positive because we don't want the volume to go negative. Now, you may be asking, well, why didn't you put brackets? Why did you put parentheses instead? Well, I put parentheses versus brackets because yes, I can touch 0 and 5 on my graph, but look at what 0 and 5 represent. If I plug 0 into that volume equation, I'm going to get a volume of 0. And if I plug 5 into that volume equation, I'm going to get a volume of 0. So I can't have a volume of 0 because that means the box doesn't exist. So that's why we use parentheses, because it's every value that's bigger than 0 but less than 5. So it's 0 to 5. Now let's talk about what the relative max coordinate represents. The relative max coordinate gives me the x value that maximizes the volume. So the relative max is the x value that maximizes the volume. So that's telling us that if I cut 1.811 inches off each side of my cardboard sheet, then I will achieve a maximum volume of 96.771 cubic meters. So again, that relative max tells me the biggest cut I can make that will give me the maximum volume. So what are the dimensions of the box? Well, remember the x represents not only the height of the box, but it represents what you're cutting off each side. So I am cutting off 1.811 inches from each end. So remember, length, width, height. My length is 12 minus 2x. My width is 10 minus 2x. And my height is x. So if I plug in 1.811 for each x value, I end up with a length of 8.378 inches by 6.378 inches by 1.811 inches. And that gives me a maximum volume of approximately 96.771. Now, you may be looking at this and you're like, why isn't the volume greatest as x approaches infinity? So why can't I look over here at that part of the graph, and why can't the values past 6 give me an even bigger volume? Okay, so like 6 is the other place where the volume is 0. So, but bigger than 6, my graph is still growing and increasing as x goes to infinity. So let's say, for example, we're just going to pick any value that's bigger than 6. So I've picked 10. So if I do 12 minus 2x and then 10 minus 2x, well, 12 minus 2x, if I let x be 10, 12 minus 20 is negative 8. And then 10 minus 20 is negative 10. So even though it looks like the volume is going to continue to be positive, what's going to happen is it's going to cause your side links to go negative. So anything beyond that last zero, that yes, it looks like if we look at the volume as a whole, it would be positive. But when we take those side links, like let's say I cut 10 off of each end, then that's going to produce a negative side length. And we can't have negative side lengths. It doesn't work that way. All right, so that's why we cannot have side lengths that are bigger than 6. And I know what you're thinking, well, a negative times a negative makes a positive. And while that is true, you've also got to look back at the individual side lengths. So when you plug in anything that's bigger than 6, it's going to produce a box that has dimensions that are negative. All right, so that's the end of this slide and this lesson. So your homework is to go work on the worksheet 5.5. Now, that is not only a practice over this lesson, it's also a review of the information that's going to be on your test next class. So make sure you complete all of it. The answer key is posted as well. If you have any questions, please visit with your teacher, and we will see you back next time for the new unit 5C1. Have a good one, everybody. Please be safe, make good decisions, wash those hands, wear your mask, socially distance, stay 6 feet apart, so that hopefully we can all be back together again soon. All right, have a great one, everybody. Bye-bye.